So it goes like this. Over on the right, I put delta x, x. So what's that? That's x, oh sorry, delta x. So what's that? That's x comma x. And now I map into it by a comma b. So what's that? That's a map from a into x and a map from b into x. Well, so now I'm asking for a left adjoint to delta, so that would have to be something here and a map into x. Well, we know what corresponds to pairs of maps like that, out of A and out of B. It's exactly, it's exactly A plus B. That's the universal mapping property of A plus B, isn't it? That a map out of A plus B is a pair of maps, one from A, one from B. So the coproduct here lives on the left. And now it's time to, maybe I shouldn't erase that. And now it's time to, there's that, A plus B. And now it's time to say something here about the uniqueness of adjoints, because it's quite important. These things that I'm producing here are things that before I characterized in terms of universal mapping properties. And I emphasize that every universal mapping property determines its object uniquely up to isomorphism. Well, it's no coincidence that these things are all adjoints, because adjoints are unique up to isomorphism. So that's the important fact that we need to know, and that's what underlies the idea of adjointness as a construction principle or generating principle for new mathematical constructions. Is whenever you have a given operation or functor, and then you ask for an adjoint to it, that's a condition on a construction, namely being adjoint to an existing thing, which will determine that thing uniquely up to isomorphism. That is to say, to put it differently, often you have a very trivial or maybe even unnoticed operation like this one of doubling something. And then the condition of being adjoint to it will be an interesting and important construction. And that construction is uniquely determined up to isomorphism by that condition that it's adjoint to this other given thing that you haven't even been paying attention to maybe. So the fact is, adjoints are unique up to isomorphism. So you can define something by saying it's adjoint to this other given thing. Yeah?
And it looks like it's used in this, or it relates to the one that we have.
Yeah, that's good. So take C and now take the up everywhere, and this product will go to the other side, and this one will come to this side, and this will become a right adjoint.
Does this work for other adjunction pairs?
It works for some, not all. I mean, you can always take an adjunction and dualize it and get an adjunction. But you can't always get some new further thing over on the other side. That's special condition. So what does it mean, unique up to isomorphism? Let's do it like E and F and D and G and say G1 and G2. And I want to show, and both of these guys are left adjoint to F. Then I want to show that G1 and G2 are isomorphic. That's what it means to be that adjoints are unique up to isomorphism. Well, again, how am I going to show it? Let's try the Oneto lemma. If you don't know what to do, that's always a good thing to try. So let's try, I want to show that G1 of, say, Y is isomorphic to G2 of Y. So let's try HOM X G1 of Y. Oh, but that's a right adjoint. So let's get it out of the way. Fx of Y. But there's some other right adjoint of F, namely G2 of Y, by the assumption that those things are both right adjoint. And so we've shown that HOM G1, of course we have to show that this is natural, but we're assuming that the adjunction is natural. That's part of the definition. So there we go. And now Oneto gives us what we want, right? By Oneto. G1 is G2. Mm-hmm.
In the diagram, yeah.
Okay, so we can use adjunctions to describe or axiomatize, define constructions in terms of other ones. Let me see, what did I want to do next? Yeah. Before doing some more examples, let me observe that there is an interesting consequence here of this characterization. Accompanying any adjunction are some distinguished maps that are, of course, important. So given an adjunction, say F left adjoint to G, let's look at the following. Suppose I take f of x above the line here. So, of course, f of x into y corresponds to x into g of y, right? But let's put in, as our y, let's put in f of x itself. And we'll put in here the identity map. Yeah, that's a valid entry for here. And now down here, I get a map from x into g of f of x. So whenever I have an adjunction, for any object x, there must be a special map like this. And this map, which is conventionally called eta, is called the unit of the adjunction. Unit of the adjunction. And of course, there's a similar thing I can do. I can say, let's put in g of y here, g of y. And then up at the top here, I get f of g of y going to y. So for every object y, there's a special map like this. That one's called epsilon, and that's, of course, the co-unit of the adjunction. So let's see some examples of these units and co-units, because these are going to be, obviously, maps that are somehow interesting. So, for example, in our case of product with A being left adjoint to exponent by A, if we compute the co-unit, what we get is the following. This is our F. This is our G. So we get, for any y, a special map, y to the A cross A, right? Because that's F of G mapping down to y. Hey, look at that. That looks familiar. That co-unit of the product exponential adjunction is evaluation. The evaluation map that we all know and love is distinguished as the co-unit of the product exponential adjunction. I have to leave some homework exercises for you, so you'll do the unit. Okay? How about the delta is left adjoint to the product? Let's do the unit. So that's our F, that's our G. Let's calculate the unit of that. So for any x, we have to have a map into the pair x comma x, and then we apply the product. We get x comma x. What could that be? The unit of the product adjunction is, of course, sometimes called the diagonal map, the map which takes every element in x to its pair x comma x. Diagonal. What's the co-unit? Well, I'll let you work some of these out. The co-unit is going to be a pair of maps because it lives in the category C cross C, and though it's of course going to be the two projections from the product. That'll be the co-unit. And then, of course, there are the units and co-units for the sum as well. So anytime you have an adjunction, you're going to want to ask yourself, what's the unit? What's the co-unit? Because these are going to be important maps. All right, let's go on now to some more examples. Good. So what I want to do now is some adjoints in logic. Well, we already saw before that, for example, if we look at the propositional calculus, we can characterize conjunction as a product in the category of proofs or the category of provability, right? But now we know that products are adjoints. So of course we have the product, right, with its usual rule, say that the usual rule for products we could express, for example, like this. We could say, let me do it like this. Let me start over a little bit. Let's set up a propositional calculus like this. We'll have expressions of the form P entails Q, and we'll have a calculus of such expressions, binary sequence. Yeah? And our axioms will be the following. We'll say it's reflexive, it's transitive, and then so the propositions form a category, and now we'll start stating our rules of inference motivated by or led by the idea that the logical operations are all examples of adjoint functors inside this category. So for example, for conjunction, we'll use the usual product rule. We'll use the usual adjunction characterizing product to give us the rules for conjunction. So we'll say, for example, phi theta. How do I want to do this? No, I want to do it the other way. I want to do a two-way rule of inference that says if theta proves phi and theta proves psi, then theta proves phi and psi. There we go. So that's the rule for conjunction. For disjunct, so this is just saying that we have the usual product adjunction now, right, with the product on the right and the delta operation on the left. And similarly for the coproduct, we'll go the other way as a two-way rule of inference again. So there's a calculus for product disjunction. Of course, we can put in I haven't talked much about the terminal object, have I, or the initial object, but these are examples of, I can put in anything here really. These are examples of simple adjunctions. I'll let you work them out yourself. The adjunction that characterizes a terminal object or an initial object looks like this. Terminal object. I defined this before, didn't I? Terminal object. One in a category. Did I say that? Okay. How do I define a terminal object as an adjoint functor? Look at the functor, which for every category takes the category down to the one object category. It takes all the objects in here to the one object in there. And it takes all the arrows in here to the identity arrow on that one object, right? So that functor, I claim, has a right adjoint, and that right adjoint picks out a terminal object in C. So that is to say, for anything in C, there's an arrow to 1 just in case this of C maps to the unique object in this terminal object category. So there's that, and there's that. So C has a terminal object if and only if this unique functor, which exists for every category, has a right adjoint. And similarly, it has an initial object if this thing has a left adjoint. So there's the description of these things as terminal and initial object as adjoints. And then the only thing left is the implication, and we know how to do that. That's phi psi proves theta if and only if phi proves psi arrows theta. So that's the whole propositional calculus in terms of 1, 2, 3, 4, 5 adjunctions. Let's continue now and look at the quantifiers, because that's, I think, a really beautiful insight due to Levier. Actually, this analysis of adjoints in logic is due to Levier, I should say. F.W. Levier. And the emphasis on adjunction as a foundational notion is also due to Levier. Although he didn't discover adjoints, adjoints were discovered by Daniel Kahn in the context of algebraic topology. There's a beautiful paper by Levier called Adjointness in Foundations, where he lays out all of the basic foundational operations as adjoint functors. I definitely recommend it. (1964), something like that. So let's do quantifiers as adjoints. So let's extend our calculus now to include formulas with variables, like predicates with individual variables. So we have some domains of individuals, and then we have some primitive predicates or relations over those individuals, maybe including the identity relation. And then we build up formulas involving some variables, right? C, x, y, etc. In the usual way, right? Maybe we say for all x, there exists a y such that r have some primitive relation here, implies there exists a z such that p of z, something like that, right? So we make some first-order logical formulas like that involving variables and quantification and the other propositional operations. And now let's look, and then we're going to have a calculus or a deductive system as before. Of entailments, phi, x, psi, right, with possibly several variables here. That I don't mean to suggest some restrictions here. Psi. Y. We'll keep things binary just to keep it simple here. So we have a deductive system of such entailments and then some rules of inference that we use to manipulate those. And now let's consider the following. There's an operation a very trivial operation of adding a new variable to a context. What do I mean by that? Well, if I have phi and I think of this as a formula in these variables, then I have, so this is a formula, say, in variables x1 through xn. Well, then I can think of this also as a formula in variables x1 through xn, and a new variable y, which doesn't happen to occur in phi, but I can regard phi as a formula in more variables, x1 through xn. And what do I mean by regard it as a formula in more variables? Well, what I mean by that is I can compare it to other formulas that might have that additional variable in it. Like I can consider implication x1, xn, y, a relation of implication to a formula that does have a y in it. So it may be that although phi doesn't have a y in it, so it lives in this set of formulas with variables at most in here, it also lives in this set of formulas with variables at most these. Good? And now the operation of regarding a formula as having more variables than might occur in it is the fundamental trivial operation that we're interested in, because this operation has adjoints. So for example, the right adjoint here of that trivial operation is the universal quantifier over y. Let's see that that's true. Let's suppose that phi of x1 through xn does entail psi of x1 through xn with a y in it. Well then, the rule of inference for introduction of the universal quantifier says that this holds for all x 1 through xn y. Everybody recognize that rule of universal introduction? The rule of universal introduction, the way it's usually stated, says if you can prove this thing from assumptions that don't involve y, then you can prove it for any y. And moreover, you can go back. Because if you can prove this for all y, well then from this you can prove this by a universal elimination, and so you can prove this. And so we've just shown that this trivial operation here, which I'll call star, is left adjoint to the universal quantifier. Now, of course, the next thing we're going to look for is maybe there's another adjoint here. What could it be? Let's set it up here. So it says if we can prove from phi x1 through xn. And now we've got some psi over here, x1 through xn, with a y in it. If we can prove from an assumption involving a y something that doesn't depend on the y, right? Isn't that exactly the existential introduction setup? E y psi x1 xn y proves phi x1 through xn. And again, if we can do this, then we can do that by a universal introduction. So of course, this is the existential quantifier. So the quantifiers in first order logic are left and right adjoint to this trivial operation of regarding a formula as having another variable in it. And moreover, because of what I said before about the uniqueness of adjoints, all of the fundamental properties of quantification are determined by this fact. This uniquely characterizes the quantifiers. And the quantifier rules of inference, including the tiresome bookkeeping side conditions on variables, right? When you learn the deductive calculus for first order logic, you have to remember now no y in psi, or what is that bookkeeping side condition? Those things are not a nuisance. Well, they are a nuisance, but they're an essential nuisance, right? You need to have those rules in order, those bookkeeping conditions, because that's what the quantifiers are adjoint to, the presence or absence of variables in the given context. So that's the specification of the quantifiers. And of course, the things I mentioned before, things like this, for all y psi of x, y proves psi of xy. This is, of course, the co-unit of that adjunction, right? If you ask yourselves, what are the units and co-units? They're going to look like this. That's the co-unit. Psi x y proves e y psi. That's the unit of the existential adjunction, and so on. Okay, so that's the quantifiers as adjoints.
Is there an off hidden in here? Because it looks like you applied the functor to the right-hand side of both and to the left-hand side of both, as opposed to crossing.
Did I do something wrong? Let's see. So let's look at the universal is on the right, and this thing is on the left. So here's this going into here, and then on the right, there's this one.
So you've got...
So the star operation goes from here to here.
That doesn't apply to the star operation.
This applies to star operation. This is formulas with at most x1 through xn free.
Yes.
Above the line.
Yes.
This is formulas with x1 through xn comma y free. This is formulas with at most these things free. The fact that this thing doesn't actually have a y in it says that it's in the image of the star operator.
Ah, okay.
Yeah? That's kind of that's the overlookable, kind of trivial operation to which quantification is adjoint. Now, there's another story that I could tell about this is provability in first-order logic. Right? There's another story that I could tell about the proof theory of first-order logic. And what that would give us, in the same way that the proof theory of propositional logic gives us the simply typed lambda calculus, what that would give us is the proof theory of first-order logic. What is that? So I think I'm going to finish up by making a big table here, and then we'll call it good. The proof theory of first-order logic is dependent type theory. Right? So there's another story that I could tell about the sigmas and pi's, which are the propositions as types, dependent type theory version of the provability quantifiers for all it exists. In just the same way as conjunction and implication are the provability versions of the proof theory in the lambda calculus that is product and exponential. Is that an analogy that makes sense to everybody?
Can you take that one more time?
Yeah. I think I'm going to make a table, and then maybe it'll work out. So, first of all, let's look at propositional logic. See if we can fit this in a table like this. So on the one hand, there's provability. By which I mean just the idea that P proves C without P proves Q, say, without knowing why. And then there's the actual proof theory of this notion, proof theory, which is really the same thing as type theory, simply typed lambda calculus. So what's that? Well, that's saying something like, take an assumption U of P, and from that, get a proof term T of Q. So that's the Curry-Howard, if you like. This is provability, just there exists some proof. This is the actual calculus of proofs. Good? Everybody's familiar with this, I think. So from a logical point of view, what do we have here? We have here propositional logic. So something like maybe intuitionistic propositional calculus. So it's got conjunction, it's got implication, maybe it's even got disjunction. Okay? From a proof theory point of view, we have the proof theory of this. So we've got type theory. This is simple type theory, if you like, or also called lambda calculus with simple types, simply typed lambda calculus. So it's the lambda calculus with products and function types, and maybe also with sum types. Good? That's something everybody knows. Yep. And now what I've done is I've given you a kind of category theoretic analysis of these things in the following terms. So here's the category theoretic or the algebraic way of looking at this thing. What is this? This is a poset, partially ordered set, which is Cartesian closed, poset, Cartesian closed category. Right? Cartesian closed poset. It's really the same thing described in a different way. Or if we add these coproducts here, we have the notion of a Heiting algebra. Heiting algebra. If we go over here and we look at the whole thing, not just the provability, but the actual proof theory of it, we got the notion of a Cartesian closed category. Right? That was a category with products and exponentials. Possibly with sums if we want to put the sums in there. So what we have down, whereas this is looking at provability and this is looking at the whole proof theory, what's really going on down here from a category theoretic point of view is something different. Well, not much different, but a little bit different. And that is, this is a general notion of a category. And this is the special case of a category, which is a pre-ordered category or a poset category. Yeah? We take the category in general or the category with just at most one arrow between two things. There's another interesting adjunction that I haven't had time to talk about, but maybe you can think about it. These are sum among all the categories. There's an adjunction going like this, with the left and right like that. And that's an interesting thing from a logical point of view too, right? It takes every category to its poset reflection. And it's a really neat way of analyzing the Curry-Howard setup that you're familiar with here from a type theoretic point of view in terms of category theory. Okay, so this is a whole table for propositional logic. Let's do the same thing for first order logic and see what happens. I don't know if I can fit it in here, but I'll try. Maybe it's not wise to do it in the same place. Well, what the heck. First order logic. For first order logic here, what does provability in first order logic correspond to? Well, this is the intuitionistic first order logic, right? So it has quantifiers A and E, and then it has of course, also the propositional logic. So this was the logical point of view, and then this is the categorical point of view down here. What's over here? The proof theory. So U, P, say T of type Q. The proof theory, this is now dependent type theory. It's lambda calculus with dependent types. I don't know if people are familiar with this, or maybe it was my job to do this, or did somebody else already do it? He said a lot about this. If I had had more time, I would have been happy to do it. It's a great, very expressive and comprehensive theory. It consists of expressions like this, right? Where this type now can depend on this variable. That's the type dependency going on there. So not only can this term depend on this variable, but this type can also depend on this variable. And then you can make sums and products of such dependent types. And you get a very expressive calculus. So that's dependent type theory. And in terms of these operations, one can recover the usual simply typed operations. And usually you put in some basic types, maybe 0 and 1, the type of Booleans, maybe the type of natural numbers. So that's a very rich and expressive theory of typed first order logic. Okay, so what's the category theoretic thing corresponding to this? Well, there is, of course, a notion down here as well. I haven't had any time to talk about this. This would be the notion of a heighting category. And really, you know what it is if you know the rest of the terms in these tables. You can work out what this has got to be. Right? It's the thing that corresponds to this in the way that this corresponds to that. Now, there's an interesting space left here, right? What is the proof theory of first order logic from a categorical point of view? Here it was a Cartesian closed category. Here it's what's called a locally Cartesian closed category. And a locally Cartesian closed category is a very robust structure in the same way that Cartesian closed category is. The definition of a locally Cartesian closed category is a category E with the property that for every object X, the slice category, which we talked about before, is a Cartesian closed category. And it turns out that that captures exactly this notion of dependent type theory, in the same way that this captures exactly this notion of the simply typed lambda calculus. And there's a completeness theorem, and there's a kind of back and forth construction. And in both cases here, I'm not saying that these two lines are somehow similarly motivated or they look the same or something. I'm saying there's a very tight connection between these two lines, right? Given something like this, you can construct one of these out of it. Given one of these, you can construct one of these out of it. And the operations, if you compose them back and forth, will be isomorphic to the identity. So I haven't defined that yet, but that's what's called an equivalence of categories. These are equivalent categories. You make a category of these and a category of these, and these categories are equivalent. It's the same thing looked at from two different points of view. And that holds over here, too. These two lines, these represent equivalent categories. Here in this case, which is just the poset case, and here in this case, too, which is the general categorical case, there's an equivalence of categories between locally Cartesian closed categories and dependent type theories. So these are just two ways of looking at that same structure again. And maybe finally, just as a kind of application, I'll mention the fact that this completeness theorem that I told you about before for Cartesian closed categories, namely, or rather for the simply typed lambda calculus, the completeness theorem for the simply typed lambda calculus was based on the fact that the Yoneda embedding, if C is a Cartesian closed category, then we know that the Yoneda embedding from C